for chain rule, everybody should know how to do like for scalars. Here, given y is a function of u is a function of x, then we have partial y over partial x equals to partial y over partial u times partial u over partial x. Now, the question here is that we want to generalize to vectors. It's actually pretty simple. You don't need to change the form. What really matters is that we only change the shapes of the output. For example, if we're going to change x into a vector, we know the result will be a row vector here. If u is a scalar, which is a function of x, then we have partial y over partial u is still a scalar. But here, partial u over partial x, that's a row vector. Scalar times a row vector, we still get a row vector. So the shape matches. In the second case, if u is also a vector, so we know that partial y over partial u again is a row vector. It's the length of k if u is length of k. And partial u over partial x, we got the matrix. So u is the length of k, x is length for n, so we get a k by n matrix. And a row vector times a matrix, we still get a row vector here, and a shape match. That's the key thing, the shape match. In the more extreme case, both x and y are vectors. So we know partial y over partial u, that's a matrix. So that's m by k matrix. So m is the length of y, k is the length of u. Partial u over partial x, again, is a matrix. It's a k by n matrix. K is the length of u, n is the length of x. So two matrix multiplication, we get another matrix, and also the shape also works well. So now we can apply it to some examples here. The first example, we assume x and y, x and w are vectors, y is a scalar. We're going to compute the inner product for x and w, then minus y b squared. So that's called a linear regression. We're going to talk shortly, but let's look at these expressions. So the goal here is to compute partial z over partial w. To apply chain rule here, the key is that we need to decompose these expressions into basic operations. So here we introduce two intermediate examples, a and b. First, a is the inner product of x and w. B is another intermediate result. It's a minus y. Finally, we get z, which is b squared. Now for every basic operations, we know how to compute the gradients. Now let's do that here. Partial z over partial w, which can be written by three terms. The first term is partial b squared over partial b, which you get 2 times b. The second term is a constant I. It's a constant 1, actually. The last term we already talked about in the last lecture, the inner product between x and w. So we got the w. We got the x transpose here. We substitute the definition of b into this equation. We get the final results. So to apply chain rule to any expressions, the key is that we can decompose the expressions into multiple basic operations and apply chain rule accordingly. The second example, the Liebig generalized x into matrix, y to vectors. So now we compute matrix times vector minus a vector y and get the square of the L2 norm. Again, that's a scalar. So the result now still compute partial z over partial w. To apply the chain rule, similarly, we just decomposed into basic operations. The only difference here, the two intermediate results, a and b, that's the vectors right now. So nothing has been changed, but the only thing that the gradients will be matrix and a vector. The first term is 2 times transpose b. The second term, a minus y, which got the identity matrix. And the last one, partial matrix times vector over partial vector, we get the matrix itself. We already covered in last lecture. So again, substitute b results into the equation, we get the final results. Okay, so any questions so far? Okay, let's move on. So we mentioned that you almost can forget about what we teach about gradient right now. Because if in the latter we can write neural networks have hundreds of layers. If you're going to compute the gradients, you're going to apply the chain rule, which means you have 100 chain rule to apply, which is pretty hard to compute. So almost every deep learning framework will do that for you. So you write in the equations, you write a model, we can compute the gradient for you. So here we going to explain a little bit actually how it works. So auto differentiation is AD means we write a program, we write a Python program using NumPy, and then the system will automatically get a gradient function and compute the results. So that's a little bit different to another two concepts. One's called symbolic differentiation. So given the equation, we first get the gradient function of this equation, and then we put data in and compute the results. So far, we just do symbolic differentiations before we actually give object function and calculate the equations here. So this is what mathematics is doing. But the good thing here, yes, you get the equation, but the bad thing here, not always can get the equation. Sometimes you have a little bit complicated functions. It's not so easy to get them. The second approach called the numerical differentiation. That is, this is how gradients is defined. So now we pick a very small number of h, evaluate fx plus h and minus fx. Then if we choose a very smaller h, we can approximate the gradients. The advantage here is that, well, we even don't know what f looks like. It can be a black box. So if you have complex functions, we have no idea how to compute the gradients, we can use this approach. But this approach can be very expensive. So if I have n dimensions, you're going to evaluate by n times. It's pretty hard to run here. So it's unlikely we can use it for deep learning because we have maybe millions of output here. We cannot apply this one by one. So here on deep learning, we are using the AD, auto differentiation. So before we dive into the detail how it works, we're going to introduce a concept called computational graph. So if you use TensorFlow before, you maybe heard about that before. The idea is pretty simple. As we did in chain rule, we decompose expression into several parts. So here we do the same thing. Given an expression, we decompose it into several basic operations, and then each node presents an operator or input. Then we build the DAG to connect this node. The arrow here means the data will be reused by the operator. So let's still take the previous example. So we're gonna compute the z equals to something. Here we introduce two intermediate results, A and B. So we present as two nodes here. And the final result is the z equals to b squared. Also, we put the input x, w, and y here as the input node. So here, each node is either input or intermediate results with these computations. So, and the arrow here means each operator which input you're going to have. So once we have the computation graph, we can do the AD. Usually we don't build by hands. Usually the deep learning frameworks will build that for you. There's actually two approaches. The first approach is called symbolic computing, or anything you can call about. What TensorFlow, CNO, and MSNet doing. So for example, in MSNet, we have the module called a symbol. It's a thing, short for thing. Here we show 3 lines for code here. We first create two variables, A and B, which is a symbol. It's a variable. We don't have data yet. Then we build expression C equals to 2 times A plus B. Up to this point, we just build the equations in the library. Later on, we can give A and B data to evaluate. So in this way, we first construct the expression and then do something else. That's the dominant way, like maybe 2 to 3 years ago, because deep learning guys don't know how to do more natural things. The other approach is called imperative. We can build the computation graph implicitly. So here, still the same program. We first create variable for the ND array called A, create a variable from an ND array called B and do the computation here. So that's a more natural way how you use NumPy, use Python to do things. So you don't need to think about what this graph you're going to build. If we put this 3 lines program on the scope called autograd.record, the system will trace the computations we have and build the computation graph at the back end. So later on, we're going to compute the gradients. We can have this computation graph there. So in MSNet, you need to put everything in the record scope. The reason is because building such graph can be expensive. You're going to install everything here in the memory. So in default, we cannot trace the program here. OK, so then once we have the computation graph, we can apply the chain rule to get the gradients. So here, we assume the chain rule can be written down by like n intermediate results, U1 to UN. So then we have 2 ways to compute the graph, to compute the results. One's called forward pass, one's called reverse accumulation. In the forward accumulation, we first evaluate partial U1 over partial UX, partial U1 over partial X. Then we times with partial U2 over partial U1. Then we going forward until we get a partial Y over partial UN. So that's kind of a natural way how we calculate the expressions. On the other approach, we call reverse accumulation. In the spatial case, it's called backpropagation, which is pretty famous in deep learning. Is actually we first evaluate partial Y over partial UN. Then we times the result with partial UN with partial UN plus 1 and move forward until we get partial U1 over partial UX, partial U1 over partial X. So then we finish the computation. So any questions so far? Yeah, question. Yeah.
So how does it actually speed up the process? I mean, each computation seems to be easily carried out numerically. Because say if Y is a vector and UN is a vector, then we still need to do like n squared numerical calculations.
Okay, so we're gonna talk about lib on the next slides. So another question?
Is one of them parallelized better than the other in terms of forward or backward?
So you mean the parallelizations?
Yeah.
So yes, let's give an example first, and let's talk about parallelization later. Any other questions? OK, so let's see a concrete example. So still, given the previous example we already have the computation graph built, and we already evaluate this graph. We call it forward pass. Now the goal here is to evaluate partial Z over partial W. So we call it this backward pass, because we start from the top node until the bottom, until the leaf. So the first step, we're going to evaluate partial Z over partial B. We know the result is 2B because the definition of definition of Z. Here, because we need a B, if we save the B result in memory or in any place, we just reuse the memory. We use the result we compute on the forward pass. So the solid cycle means we're going to read the data from the output of this operator. The dotted line means there's data dependencies between these 2 nodes. So now we move left. We're going to compute partial Z over partial A, which is equals to partial Z over partial B. This is the result we already computed before. And then partial B over partial A. By the definition of B, we know this is 1. So we actually just read the result from the previous node. Finally, we're going to compute partial Z over partial W. Again, we can decompose it into the previous results, partial A over partial A, partial Z over partial A, times partial A over partial W. That's by the definition of A, we know this is X transpose. So what we're doing here is just to put the result from the previous backward node and the input node of the forward pass, and do a matrix multiplication here. So to answer the previous question, how AD, you don't need to numeric evaluate things, because we know the definition of each operator. For we can compute symbolically the gradient of this operator. So this actually, within the graph, within the node, we do symbolic differentiation. So this usually you have an efficient way to compute things. The second thing, if we want to run in parallel, well, this graph you don't have so much parallel. The only thing here, for example, if you're going to evaluate the bottom left nodes to leaf, then you can run two leaf in parallel. But there's a chain rule here. So, but in deep learning, usually the graph is more complex. You have multiple paths. You can run the paths in parallel. The other thing that, because each node is like tensor calculation, this is usually a large matrix multiplication, we can run parallel within this node. In most cases, in deep learning frameworks, we run the parallel within the node. Parallel within the graph, you can do multi-GPU training. We're going to talk about maybe, I don't know, maybe 4 weeks later, we can run parallel multi-GPUs. But on a single device, usually we do parallel within a node. OK, any questions so far? Question? Yeah.
So I'm still not sure. Like, do you first evaluate the forward pass and then substituting back in backward pass? Because the way you presented it, it seems like we're just going through it like that.
Oh, you mean how to define the
Just evaluating the forward pass and just substituting back in the backward pass.
Oh, you mean usually what we do is we first evaluate the forward pass. We store every result on the forward pass. And then we start from the backward pass from the back. In the forward pass, bottom to top, and the backward pass top to bottom. But all the forward pass, the results are stored, so we can reuse later. OK, so then next, it's like a quick summary. How to do AD is that we first build a computation graph, then run a forward pass, and save all the intermediate results, and then run the backward pass so we can evaluate the graph in the reverse order, and then replace each operator by the symbolic gradients of the forward pass operator. And then one thing I want to mention here, if you only compute one gradient here, if you don't need a gradient over if we don't need a gradient over x and gradients with respect to y, we don't need to evaluate this path here. So we can only evaluate partial of the graph. So that kind of saves you a little bit of computation overhead. Question?
So because we're like doing all of these intermediate steps, and like does the end product always contain the intermediate variable?
Usually we don't. The framework will store all these intermediate results in the back end. You can get these results, but usually we don't tell users how to do things. So usually we do is here, we put the intermediate result in the memory, and after backward is done, then we can ignore these results. OK, so question?
Do we do this every time we change this W?
Yes, every time you change W, you need to evaluate the whole graph. But if you don't change the shape, which is you don't change the input shape, all the memory can be allocated before. So allocating memory, especially on GPU, is pretty expensive. We can put the memory, the GPU, you're going to see a very high memory usage, but you save your time. Yeah. Also, if you decrease the size, you don't need to allocate memory because you have enough memory. The only thing happens is that next time you're going to use a large X into the network, then we're going to reallocate all the memories. So let's do a quick analysis of the complexities. So the computational complexity is OM, nth number of operators we have. So usually nth number of layers. So if you have 100 layers or 100, usually it's pretty similar to the forward pass because the symbolic definition of the operator is usually pretty similar to the forward pass. So which means if you spend 1 second in the forward pass, you usually spend 1 second on the backward pass. But the key thing here, we have a little bit of memory problem because we need to store all the intermediate results on the forward pass. So that causes you a problem if you have very long, very deep networks. And if you have large batch size, you got a problem here. So I'm going to talk a little bit advanced topic. How do you reduce the memory? In most cases, you don't need to worry about that. But if you really run very large applications, for example, you're going to run object detection on the 4K video, which is what self-driving cars doing, then you maybe have a memory issue here. Still, the question is here, you have the memory is linear to the number of layers you have, and the linear to the batch size you're going to have. We're going to talk batch size maybe half hour later. But we have, if you're going to use GPUs, each GPU only have 32 gigabyte memory max. Then you have, it's much slower than CPU memory, which is usually 1 terabyte right now. So one idea is here is called trade computation for memory. The idea here, we only save a part of the intermediate results, and just ignore the others. If we're gonna need this result we didn't save, we just recompute it. Okay, that's a normal thing actually for compilers. Let's look at a concrete example here. Assume we have very simple paths for the computation graph, and the backward is also a path. And this solid line means data dependencies. So the first thing we're going to do is like we partition the graph into 2 parts. So 3 nodes in one part, 3 nodes in the other parts. In the forward path, we only store the first node on each path, on each part. So which is the solid circle, we store the results. And we ignore the results on the normal circle after we have computed for the path. Then to compute the backward path of part 2, because we don't have the results, we need a result for the top 2 nodes, but we don't have it. What we can do is that, like, we just recompute from the head node, or which is the bottom node of this part. We just recompute these 2 results here. And to value the last part, we also recompute the top 2 nodes results on the part 1, so we can get the thing done. Okay, so any question here? Question?
Sorry, does the single link mean that only one variable is needed for each calculation?
Yes, the link means data dependencies. So if, so for example, just to hire, yes, on the forward path, every node only needs the backward node, the node after that. In the backward path, each node needs 2 nodes for the inputs.
So if there are more links, say if it's a binary structure, then you need to store more data to recover your process.
Yes, the question like, if you have like graph, yes, you need more data. But in most cases, deep learning is a chain rule. You stay layers by layers. You don't have a very complex, fully connected graph. If you have such graph, you don't have anything to save. Okay, so again, the complexities, we need additional forward paths. The reason because for the backward path, at most we need to evaluate the whole thing on the forward path. But the lucky thing here, well, let's first talk about the memory save. Assume we have m parts. We need OM for the head nodes for each part. Then during each pass, we need to store the result on each part, so which is O n divided by m. If we choose m to be square root of n, so we can reduce the memory complexity from O(n) to O square root of m. So question here. Good. When applied to deep neural networks, the lucky thing is here, not every layer is as heavy as the other things. For example, we have a bunch of activation layers, which is just element-wise the computation. For example, just the max, x, and 0, such simple results. We usually can ignore these results. And for computation-heavy layers, fully connected layers, we're going to talk about later, is matrix multiplication, or the convolution layers, we save these results. So in this case, in practice, even we only throw away the simple layer results. So as a result, we can get at the most 30% of additional computation overhead. But now key thing here, we can train 10 larger network given memory GPU limits, or use an 10x larger batch size. So that's a key thing usually to a lot of computer vision problem if you do 4K videos, 4K images, or sometimes like if you're going to use batch normalization layers, you want batch size not to be small. Question?
How does the speed up for larger batch size compare to the speed cost for additional computation?
Not too much, actually. If in practice, if you have enough GPU memory, then you use all of memory, which means you usually have a large batch size. Then increase the batch size from 1 to 20 can also give you 2 times speed up. But increase the batch size from 20 to 100 usually don't give too much speed up. So in most cases, we use the batch size in the normal stages, 20, more than 20, so you don't see too much things. But the more thing here, here is the large batch size sometimes give you more stable training results. Questions? Okay.